Hello, fellow sailors. Today I'll be discussing 4 critical issues that every sailor must understand about electrical power systems aboard their vessel. These fundamentals will help you maintain reliable power and avoid potentially dangerous situations at sea. Different electrical equipment aboard our sailboats have dramatically different power requirements. Your bilge pump might draw only 3 to 5 amps, while your electric anchor windlass can demand 80 to 150 amps during operation. Consider your refrigeration system. It cycles on and off throughout the day, drawing 5 to 9 amps when running. Navigation electronics like your GPS and chart plotter are relatively modest consumers at 1 to 3 amps each. But here's where it gets interesting. Your electric winches can pull 60 to 100 amps during heavy loads. This vast range means you must carefully calculate your total electrical budget. A common mistake is underestimating simultaneous power draw. When multiple systems operate simultaneously, perhaps your refrigerator, autopilot, navigation lights, and instruments, you might be drawing 15 to 20 amps continuously. Secondly, marine batteries have finite recharge capabilities that directly impact your electrical independence. Unlike your home electrical system with unlimited grid power, your sailboat operates on stored energy that must be replenished. Lead-acid batteries, still common on many vessels, typically require 6 to 8 hours to fully recharge using proper charging profiles. They can only accept charge at specific rates, typically 10 to 20% of their amp-hour capacity safely. This means a 400 amp-hour battery bank can only accept 40 to 80 amps of charging current without damage. Lithium batteries charge faster but still have limits. Even with their superior acceptance rates, you're looking at 2 to 4 hours for a complete charge cycle. Here's the challenge. If you're drawing 50 amps per day but can only generate 30 amps through your solar panels or wind generator, you're operating at an energy deficit. Your engine alternator might produce 100 amps, but you need engine running time to catch up. This finite recharge time forces you to balance consumption with generation capacity and plan your electrical usage accordingly. The third issue centers on understanding that your DC battery system is fundamentally a chemical process, not just an electrical storage device. This chemical nature creates unique challenges and limitations that affect your boat's electrical reliability. Battery chemistry determines performance characteristics. Lead-acid batteries suffer from sulfation when deeply discharged, permanently reducing capacity. They also have memory effects and require specific charging voltages, typically 14.4 volts for bulk charging, then 13.6 volts for float charging. Temperature dramatically affects chemical reactions. Cold weather can reduce capacity by 20 to 30%, while excessive heat accelerates chemical breakdown. AGM and gel batteries have different chemical compositions requiring different charging profiles. Lithium batteries use entirely different chemistry with built-in battery management systems to prevent overcharging or thermal runaway. Each chemistry has specific depth of discharge limitations. Lead acid should rarely go below 50% capacity, while lithium can safely discharge to 80%. The chemical nature also means batteries age and degrade over time. Cycle life varies dramatically. Lead acid might provide 300 to 500 cycles, while quality lithium batteries can deliver 3,000 to 5,000 cycles. Understanding these chemical processes helps you maintain battery health and predict replacement schedules. The fourth critical issue involves protecting your electrical distribution infrastructure from overcurrent conditions that can cause fires or equipment damage. Marine environments are particularly harsh on electrical systems, making proper protection essential for safety. Your electrical distribution starts at the battery and flows through main distribution panels, sub-panels, and individual branch circuits. Each component must be properly sized and protected. Wire gauge selection is critical. Undersized wiring creates resistance, heat, and potential fire hazards. A 30 amp load requires 10 AWG wire for runs up to 10 feet, but 8 AWG for longer lengths. Overcurrent protection includes fuses, circuit breakers, and sometimes both. Main battery disconnect switches should handle your maximum load plus 25% safety margin. Branch circuit protection must match wire capacity, not equipment draw. Your 15 amp autopilot might run on 14 AWG wire, but the circuit breaker should be 15 amps to protect the wire, not the equipment. Marine-grade components resist corrosion and moisture. Tinned copper wiring, sealed connections, and proper routing away from bilge water and engine heat are essential. Understanding these 4 electrical issues, varying power demands, finite recharge times, chemical battery architecture, and proper distribution protection forms the foundation of safe, reliable marine electrical systems. Hopefully, these tips will help you sail with more ease.